tutorial of MLIR. It has 7 chapters from chapter 1 to chapter 7. Today I'm going to transcribe chapter 2. The chapter 2 folder is like this. It has a toy include folder, which has AST and dialect lecture, MLIR generation, operations definition. It's the TD file is basically the language defined by MLIR, and parser.h is about parser. So I think I'm quite familiar with the AST, lecture, and parser, so I'm not going to type these in, but I'm going to type in ops.td and also dialect.cpp, mlirgen.cpp, quite long. And also parser, I'm not going to type these because I'm quite familiar with the AST, parser, and lecture. I'm not familiar with is ops.td and mlirgen, dialect.h. So these are something I have to type. Let's get started. Also, I have copied the chapter 2 folder to tr2, so I can build the project by running this command. Before doing that, I'm gonna add my camera. Okay. Now you're ready. Let's go. So from where we should start, how about ops.td? Ops.td is basically defining the dialect itself, and then defining operations, which is extending from op class. And then finally, these operations are used in other source codes, and this TD file generates a CPP and header file. So I think this is the core file of this project. So I'm going to remove all of them and start typing them. Okay, remove all. I have my iPad on the right side, but I cannot show it to you here, but I'm reading source code from there and then typing it. Interface here is like a trait, so it describes what kind of feature is a operation or dialect has. Simple interfaces. Side effect interfaces, and then I'm going to define toy dialect extending from dialect select, and its name is toy. Namespace is MLIR toy. Fold API. Fold. I don't know what this is. Next, we will type in a base class for operators. The memory here is the name of this operation, which is used in text files, and traits describe features or let me characteristics of an operation. This is constant operation. Pure. Pure means it will be if that it is not used. So it has a summary. This is for generating documentation. Constant. I'm going to skip description. Or I'm simply copy this because it doesn't make sense to type in this except the source code. So let me copy all of them and then just type this source code because this is meaningful to type. And its type is tensor 2 by 3 by 64 bit float. Okay. And it's time to define arguments and the return type. Arguments start with the ins something and results start with the outs. So ins, it's F64 elements ATTL. F64 tensor. This is elements ATTL because it's not not just a normal argument, but it's embedded into the source code and it doesn't change at all. For example, this is a source code. This is a constant defined in source code like this, and this is from attribute instead of argument. So MLIR has two different kind of arguments. One is attributes, that is not changing, arguments that are not changing, and the actual argument that are changing is passed into argument. But in this case, it's constant, so we will use the constant values for initializing constant operations. So we are using elements ATTL. And functions for building this operation. There is type something like this. We will type the source code here, but before doing that, let's see the structure of the builders section. The easiest one is having one argument. So double here is a type and value is the argument. And it doesn't have any implementation, so okay. But the first one provides an implementation, so we have a bracket here. Argument is dense elements $value. Dense elements ATTL is type. So we're gonna call build method state value of attribute. Okay, it's great. This is something I cannot read from this original source code. So I strongly suggest you to type some source code that you want to learn, because Copilot is going to teach you. Next one is add up. I think we first have to see the source code of a toy language. It is a very simple language, like this. Example language is here. So what you want to do is add operation. I'm not sure where the add operation is used, but element-wise addition operation. So basically we have tensors like this, and adding two tensors, the operator is doing adding two tensors element-wise. Let's type in toy up operator, summary, description, arguments, results, has custom assembly format equals 1, builders, is something. So this is basic format. Summary, element-wise, description. I simply copy them. Description and arguments is F64 answer. Basically, we have two arguments here. It's binary operator. Results, it's out. Answer. Looks great. And finally, we have it. We have the builder, but we need two arguments. One is LHS with the value type. Second is RHS with the value type. Okay, we are done. Next one is func OP. I'm not quite familiar with this summary description arguments field, so I'm gonna type in until I get accustomed to these names. Func is basically function here. We are defining a function like a def something. So this function is gonna be an operator in MLIR. So I'm gonna type in the definition of functions like this. Type in the operation related to defining functions like this. So def func of poi on and you have traits here. Two traits. One is function of interface. Looks like these traits are describing the function of interface defined by the source code of MLIR. But I'm not sure if it is defined by us. We will see. And isolated from above is looks like variables are isolated from above. For example, if we have some global variable here, not global, but I'm not quite sure what this is, but it looks like the scope is isolated from above. We will see soon. And again, we have a summary, description, summary. Arguments, regions, builders, extra class declaration. And finally, I'm going to copy some of the source code from here because about the description. It's too long to type, taking too much time. But this part I'm going to type in because it's important. Summary. User-defined function operation. The prefix here is the dialect name, and the function is operator name. And from here, function definition starts. You may wonder why this is different from the function definition here. This is defined by user, and it is read from the lexer and parser, and then transformed into AST, and then abstract the syntax tree, and then it is converted to MLIR format, MLIR dialect format, which is the program I'm going to type. So you can think this dialect is about transforming the AST into MLIR dialect, which is we are typing right now. %0 constant. This is the attribute. 5.5 and 5 zeros. E plus 00. Answer of 64-bit float. The tensor type is a built-in type in the built-in dialect. Toy.reshape %0. The %0 here is referencing the return value of the previous statement. Two by 64-bit float. And we have a new function called the toy print, which is an internal function we're going to define. %1 tensor f64. So finally, we will gradually transform this MLIR dialect into lower dialect, something like LLVM dialect, and then it's going to be converted into assembly code of CPU or GPU. So what you have to do is provide the transforming functions and also dialect functions like this. Toy dialect is a new dialect we are going to define. So we started defining toy dialect here. Next, we will describe. Let's try to remember what we have learned. I'm typing without looking at the source code. It's because it's a function. I don't know. I think I have to type because it's not just a simple binary operator. Okay, it has ins and 4 parts. The first part is symbol, name, ATPR, sim, name. Looks like a main here. And then type ATTL function type. Optional attribute is array ATTR. not fully understanding what this is, but I'm not worried about too much because we will learn later. Name of the symbol, name of the function, and function type, arguments, attributes, and result attributes. Looks like the argument maybe this one, maybe arguments that are written here. It's args and result attr. Okay, and then regions. It has a region, so this part is a region. Basically, it has a list of operations, and also you can have another region. For example, here we have some code like this, then an operator can have another region. So region declaration is region, any region builders function name, function type, I'm not really fully understanding what this is. Just a typing. Extra class declaration. Copy some code and then type in. Okay, we are done. Function up is having two traits: function up interface isolated from above, and description. Sample function is function main a, b. These are arguments, and quite likely this part, this optional attribute array. It looks like we can provide the optional attribute for result. Next one is a generic call OP, which is a calling operator. Summary. format builders. Summary. Description, I'm going to copy. No need to type all of them. Just copy and type somewhere I'm interested. %4 toy generic type is answer 2 by 3 by f64 answer 2 by 4 by 3 by f64 again, and then the result type is answer unknown by f64. Last time is unknown. And then we have our arguments. First argument is function name. Let symbol left quality and variadic list of arguments. F64 results. F64 tensor. Assembly format. This is the format of this assembly. Looks like this is used for parsing and printing this operation. Holy. This is a token. Assembly format. Okay. And builders. We need to curly and arguments. And type of these are we're done. Let's move on to MLIR. So the generic call is this one. This one is calling usually defined function. So this is generic call and function symbol and argument 1, argument 2. We define these as a variadic argument here. Variadic, and type is F64. All of the types in this language, toy language, is just a F64. No other type like a string or integer. Only one type, F64. So we can write it like this. Next one is MLIR. MLIR is this one. Basically, multiplying two tensors element-wise. So when you transcribe, you don't need to see the source code if you can type them by yourself. Multiplies, multiplication operation. Description, I'm going to copy them. Arguments. We have two arguments, is RHS, LHS, and RHS. Type is F64 tensor. F64 tensor. Result outs F64 tensor. Okay, we are done. Pretty simple. And now time to type printop. Printop is here in the main function. We have the last function whose argument is tensor. A tensor is passed as an argument into this print, and the tensor parameter is going to be printed. Print up, print, let summary, let description, let arguments, let assembly format. Assembly format is input here date. Type. F64 tensor. The input is, we have only one input, and its type is F64 tensor. So type of input is F64 tensor. So print is like this. Description, and then put some example of MLIR here. Avoid the print. Summary. Reshape up, tensor reshape operation. Summary. Description. Assembly format. tensor reshape operation. And this part I type in %0 toy dot reshape %1 by 1 so 10 by f64 2 tensor pi by 2 by f64. It's changing the shape of the tensor. So input should be a tensor, f64 tensor, I guess. My guess was right, okay. And the result is static shape tensor of f64. Assembly format. Okay. Oh, it's wrong. Type input attl dict to type result. Return up. Return is the return operation is used in a function for returning a value like this. Return some value for a user-defined function. And here summary. Okay, let's copy. Accept the source code. arguments. Is assembly format. Builders. The location. Extra class declaration. Return operation can either have an operand or not. So it looks like we have it. A Boolean returning function called has operand, returning true only if the get num operands is more than 0. Transpose up. I'm typing without single source right now. Summary, description, arguments. Looks like we need to have 2 inputs. Answer, LHS. Return type should be F64 tensor. Oh, I was wrong. It just has only one argument because it's a transposing input. It has only one input, and its type is value. Assembly format. Description. We don't have description here. Tensor. Okay, we are done. Next one. Oh, we are done. That's great. And if So let's just see if it compiles. Before seeing it, let's read the code carefully and see if there is any bug. This is something I don't know. Okay, let's try to compile. Folder here is in the LLVM project, and in the build folder, this is a folder I created after cloning the source code, and I ran a cmake command. The command is cat build the message like this. I ran this command to configure the cmake environment, and then I'm running cmake build toy c here two. Oh, okay, here two. Inst. We have 3 places. It should be inst, but I typed in as inst. It's wrong. So I fixed this error. I'm not sure why I have typed inst here. Inst, okay. Still, we have some error. Expected semicolon. Line 60. So Control G is go to line 60. I need a semicolon here. Another semicolon 79. 79. Let's try to see if we have any missing semicolon from here. Okay, this one. So many missing semicolons. Okay, I think I'm done. Run again. Int. Not int but ins. Int is wrong but ins is right. RHS. Okay. 49. Maybe it was not 49. 86. 89, 89. 89. Parenthesis was missing. $98. Semicolon was missing. Let's just see what's different. Funk up. I'm not sure what's wrong here. Tag in it. Oh, I see. Missing comma. Missing semicolon. Missing semicolon again. Missing semicolon again here. And here. And here. Expected comma. Means, I mean, parenthesis here. Parenthesis was missing. Generic call has some problem. Results. I think the results, the dollar should be removed from the results. Dollar sign should be removed in generic call. Let's ask to ChatGPT. results are not used in the assembly format. Oh, I think the results are not used in the assembly format. Okay. Custom assembly format. Reshape up. Oh, here again, dollar results. My fault. Okay, we are done. Oh no, it's failed. Why failed? Error. No member named. Set args ATTRs ATTL. Set arg ATTRs ATTL. Out of line. Get args ATTL name. Get args. I think I need some time to investigate this, so I will finish today's